momentum, lesson 4. What, as a starter, what is an elastic collision? We should remember from last lesson, an elastic collision, linear momentum is conserved, as it is in all collisions, but if it's elastic, also kinetic energy is conserved as well. And that kinetic energy is conserved as well as linear momentum. It's our 4th lesson of this topic on explosions, which granted is going to be the sort of lesson where it's a lot less interesting to do it as an online lesson instead of in the classroom, because we don't get to do the actual explosions. So I do apologise about that, because we'd have spent the lesson, setting off rockets across the room or something. If I get you to help out at parents' evening in autumn, maybe, when we have that, then I think that will be the time to set off the rockets. Our spec reference. Down at the second from the bottom, elastic and inelastic collisions and explosions, as well as up at the top, second, conservation of linear momentum. It's those bits that we're looking at still. We want to describe the energy changes taking place in an explosion, and what can always be said about the total momentum of a system that has exploded, and what the consequences are after the explosion if only two bodies move apart. So, explosions. When two objects fly apart after being initially at rest, in physics we call that an explosion. Granted, there's lots of things that can be encompassed in that definition that probably aren't explosions like anything that you've ever thought of. So, for instance, if I get two wooden dynamics trolleys, like what we'd use in class for forces, the little wooden trolleys on wheels, and they've got that springy thing on the back, if I put two of them together and make them fly apart using the springy thing, that's an explosion in physics. I mean, explosions are also explosions, but we need to think about scenarios where we could actually analyse them afterwards, and for us to analyse all of the objects that fly apart in an explosion, that would be quite difficult when we are only normally dealing with two objects at a time. So we're normally going for the simple examples. Could have an explosion like if it was a cannon, for instance, you could consider the cannon and the ball before and after that explosion, for instance. So beforehand, thinking about that cannon and that ball, it's inside the cannon, neither of them are moving. If neither of them are moving, they have zero momentum. So beforehand, as they are both at rest, the total momentum before is zero. So via conservation of momentum, that should tell us the total momentum afterwards has got to be zero as well. But why? Afterwards, the two objects will have momentum that is equal and opposite. So, the example, the cannon and the ball will be moving in opposite directions. The cannon has recoil, not very much, but it's really big, it's very massive, so won't move very much. The ball, much less massive than the cannon, so goes a lot faster. The momentum of both of them will be equal because of conservation of momentum, but mass times velocity, if the mass is large, velocity is low. If the mass is low, velocity is high. If you fired a smaller projectile, it would go faster, because the speeds aren't equal. So, this example again. What if we have two skaters, but as they push away from each other with their hands from stationary position, the first skater moves away with a velocity of 3 meters per second, and we don't know the velocity of the second one, that's what we're trying to calculate. So they push away from each other. Check out my animation again, amazing. u1 equals u2 equals 0. The initial velocities are 0. We know that the final velocities, one of them is 3 meters per second, and the other one we don't know. The mass of each of them, 65, 75, and the combined mass, 140 kilos. So conservation of momentum says P before equals P after, so 0 is equal to the sum of the two momentums afterwards. Now it's this difference, isn't it, because one of them is negative, because they're going in the opposite direction to the other. So m1v1 minus m2v2. If we substitute in, that will give us 0 total momentum before equals the total momentum afterwards, 65 times 3 minus 75 times v2. v2's are unknown, so we're going to solve for that. So 65 times 3 is 195. That's going to be equal to 75 times v2. Dividing by 75 on both sides gives us 2.6 metres per second. The two velocities aren't equal, as we said. The two people have got slightly different weights, 75 and 65 kilos. The one with the greatest mass, person 2, moves away slower because of Newton's second law, force is mass times acceleration. Bigger mass, it's going to accelerate less from the same force, because the force applied by both people is going to be equal and opposite, because that's what makes them move apart. We need to know one of the final velocities, otherwise we wouldn't have enough information to solve this problem. Remember, we can only solve problems with one unknown unless we use simultaneous equations. So the number of unknowns we've got tells us how many equations we would need in the case of simultaneous equations. And that's quite a hard level of maths skill for them to ask. They probably wouldn't, so don't worry. I can only say probably though, because GCSE math skills are required for this. A-level physics. Anyway, we could, however, if we didn't know both of the final velocities, give the ratio of the two speeds. So the ratio in this case would be 65 to 75, which would simplify to 13 to 15, as in the smaller one is 13/15ths the size of the larger one. So 2.6 is 13/15ths of 3. So what about the energy stored? Well, it depends on how the explosion occurred. If it was the example from the start, the two wooden dynamics trolleys with the integral spring, the total kinetic energy after the explosion is equal to the energy stored in that spring. That sort of makes sense, doesn't it? We've got to have conservation of energy. We're saying, where has the energy come from? It's come from the energy stored in the spring, the elastic potential energy. It's going to the kinetic energy of both the objects afterwards. What if it were a chemical explosion? The total kinetic energy would have to be lower than the chemical energy released in the explosion. Why is that? Because energy is going to different places. The energies might be going as heat, light, sound, wherever else. All of those things carry away energy too, so that would not be elastic in that case. Whereas the first case, the wooden dynamics trolleys, it's probably a reasonable approximation to say that would be elastic. So, plenary, that's it. What is the total amount of momentum before and after an explosion? Momentum is conserved, it's got to be the same, and if it's an explosion, they all start at rest, so momentum is 0 before and 0 afterwards then. That's the end of the momentum topic. I'll post some exam questions for tomorrow for you to do, and then next week we'll be doing our live lesson. The live lesson, as I'm explaining in your mentor meetings, will be about Young modulus and stress and strain, but more about that in the lesson. And we'll also have some Google Classroom work on the last chapter that we need to do, which is about work, energy and power, which should be quite straightforward. So I'll post some videos on that next week, along with some example problems, which will take us up to the end of the year and the end of year 12. So nice one, guys. Well done.